All right, ladies and gentlemen, let's talk about Chapter 3, which is decimals. Now, our first section deals with representation, comparison, and ordering of decimals. So let's start with some basic definitions. Our number system is called the decimal system because it's based on 10. The decimal point, which is actually called a radix point, we only call it a decimal point because we're using in the decimal number system, serves the purpose of separating whole numbers from fractions. When we use the term decimal, we are talking about a number that is written in decimal notation, which means using a decimal point, which our book does refer to as standard notation. Okay, and of course, we know places. We know how places work. We've talked about places before. We talked about places before in this very class, so I'm not going to get into places in any great detail. So when we talk about places, let's just kind of go through it real quick from left to right. We, of course, have the hundreds place, the tens place, the ones place. The decimal point is a separator. It is a barrier. It is a wall. It is what keeps the whole numbers separated from the fractions. It is not a place into and of itself. Then after the decimal place, we have the tenths, the hundredths, and the thousandths. We could, of course, have the 10,000ths, 100,000ths, millionths, and so forth as we keep going to the right. So how are we going to write things? Well, there's standard form, which is basically just writing a decimal. There's expanded form, where each non-zero place, okay, non-zero being the key word, so each non-zero place in the decimal is accounted for in a sum. And then there's written form, where we write it out verbally. Written form is literally, if you were to say this as a fraction, what would you be saying? That's what it is. So if I have a number, 3.579, that's standard form right there. If I were to write that in expanded form, it would be 3 plus 0.5 plus 0.07 plus 0.009. Okay? Now, just so that we're clear, let's say that was 3.079. I would not have a 0.0 for that place. I would just go 3 plus 0.07. So we don't include places. And let's say it was 10.579. I would say 10 plus 0.5. I wouldn't say 10 plus 0. So we do not account for non-zero, or I'm sorry, we do account for non-zero digits. We do not account for places that are occupied by a 0. And if we were to write that out verbally, it would be 3 and 579 thousandths. The fraction that we use is always the last place. The 9 is in the thousandths place, so our fraction is in thousandths. So the way this works in the homework is I give you one, you give me the other two. So let's take a look on the next slide. Of course, this is 5 separate problems, not one big problem. Pause and write them down. So 5.067. Notice how I did not account for the place with the 0 in it. It's just 5 plus 0.06 plus 0.007. And, of course, written out verbally. Now, some people will hyphenate numbers like 67. Some people will not. It is technically correct either way. All right, same thing with 3.209. Notice I did not account for the 0. I have the 0.2 and the 0.009. I do not have a 0.00 in between. And writing it out again, thousands. 7.006, again, same thing I talked about before. No 0.0, no 0.00, just the decimal 0.006, just accounting for the non-zero digits. And that, of course, is 7 and 6 thousandths. Now, the one on the bottom here, it's given in expanded form, so the first thing we do is we write it out in standard form as a decimal, and then we would write it verbally. And then the last one is written verbally, so we start by writing it in standard form and then expanded form. Now, comparison, you know how to compare numbers, all right? Basic concept, greater than symbol, less than symbol. With decimals, because there's different ways to represent them, there's also the possibility of an equal sign. But more often than not, you know, especially if you're comparing like something that's in standard form to something that's in expanded form, you know, it's probably going to be just greater than or less than, but the potential does exist for it to be equal. So what you're actually doing in your head when you're comparing decimals, whether you realize it or not, is you are starting at the leftmost place and you are comparing digit by digit. If the digits are the same, you move to the right one place and you compare again. When you finally get to the point where they do not have the same value, that's when you say, okay, I'm done. Now, If a decimal does not have any digit in a particular place, that is considered to be 0, and you can write a 0 in that place. It is always a good idea when you are comparing and ordering decimals to write every single decimal to have the same number of places both before and after the decimal point. And we do this by writing what are called leading and trailing zeros. Leading zeros are the zeros that we put in front of numbers. You can put as many zeros as you want to in front of a number, it changes nothing. Trailing zeros are the zeros that we write at the end of a number. The rule about trailing zeros is they must be after a decimal point. So if I want to turn 23 into something else, I can't just throw a 0 in there. But if I want to put zeros after the decimal point, I can write as many as I want. Classic example. Let's say we're comparing these two numbers. Now, right off the bat, there is someone out there who's going to say, okay, I see the 23s, they're the same, so I just need to compare the decimals. That's fine, nothing wrong with that. And then somebody's going to go, oh, 18 is bigger than 2, so that one must be bigger. And that is incorrect, because 23.2 only has one place to the right of the decimal point, where 23.18 has two places to the right of the decimal point. But if we were to fill in that trailing 0, now we could compare them and go, oh, the 23s are the same, but 20 is bigger than 18. However, even if we did not do that, we could take the approach of, are these digits the same? Yes, move to the right. Are these digits the same? Yes, move to the right. Are these digits the same? No. 2 is bigger than 1, therefore 23.2 is bigger. Okay? As always, take a minute, write down the word problem so that we have everything written down. Remember, when the question asks which is denser, that is the same as saying which one has the greater density or the higher density. So, okay, assuming we paused and wrote that down, what this problem is actually asking you to do at its core is just compare these two numbers. That's it, and say which one is bigger. And of course, using the skills that we just had from the previous slide, we know that 22.58 is bigger than 22.56. And the reason for that, I mean, forget everything we say about decimals, it's money. $22.58 is more than $22.56, and we know that. So in this case, osmium is denser than iridium. Once again, take a second, write it down. Just so that you know, when we're talking about this, apparent magnitude is how you measure the brightness of stars. Oh, there goes the Borg cube chasing them. So when we're saying what's the apparent magnitude, we're basically saying which star is brighter. So okay, assuming that we paused that and we took a second and we wrote everything down, all this problem is really asking us is which is bigger, 13.5 or 13.05. Again, if we go digit by digit, the 1s are the same, the 3s are the same. Oh, 5 is bigger than 0, so it's got to be bigger. Don't like that idea? Put the trailing 0 and make it 13.50. So the other star has the smaller apparent magnitude, because this problem was not asking which was greater, it was asking which was smaller. Okay. In addition to that, we have to talk about ordering decimals. Ordering decimals is just kind of like comparing decimals. But you have a lot of them. So the two main methods are ascending order, and ascending order is the one we tend to use the most, but not exclusively. It means we order it from least to greatest, from small to big. But there are cases where we would order things in descending order, from big to small, all right, from greatest to least. So make sure you pay attention to what the problem is actually telling you to do. Now, in the case of decimals, there's a lot of comparison going there, okay? Yes, you're not sitting there and comparing every single number to every other number, because the truth is that would just be a bit much. For the most part, you're basically just saying, okay, is this number bigger than this number? Great, I'll put it first. Now let me check the next one. Oh, it kind of fits in between. That's it. So here are our examples from least to greatest. Again, take a second, write them down. Obviously, we'll just write our answers down in one shot. So, okay, assuming you paused and wrote down whatever you had to. The numbers that are in white ordered from least to greatest: 1.7, 1.8, 4.15, 4.2. Now I'm going to stop right there, because if you are the person saying, wait a minute, why is 4.2 bigger? 2 is smaller than 15. No, put the 0 after it, and you are comparing $4.20 to $4.15, and you know $4.20 is bigger. With the numbers that are in yellow, 0.05, 0.1, 0.105, and I'm going to stop right there. because there is definitely somebody who's going, wait a minute, 105 is bigger than everything. It's bigger than 2 and 17 and 11. Why is that not the last one? Write the trailing zeros after everything. So everything has 3 places after the decimal point. And you'll realize that 105 is smaller than 110. It's smaller than 150, 170, and 200. The last one, same thing. What about that 101 that's bigger than 99? No, put the trailing zeros. Make sure that you write down the trailing zeros so that every number has the same number of places after the decimal point. All right? When in doubt, think of money. Money is always helpful. So think about this. 1.101, that's a little bit more than $1.10. You really going to tell me $1.99 is less than $1.10? We know better than that. Okay, so homework, fairly straightforward. Obviously, we'll answer any questions we have to in class, so we'll talk about it then. Good luck. See you in school.